We've discussed several topics associated with unconventional shale gas, oil development activities, and we've talked about how important it is to really know the area as best as you can before you start to drill. We've made important distinctions between hydraulic fracture stimulation, the microseismicity associated with hydraulic fracture stimulation, and the magnitude and energy released that's associated with induced seismicity or wastewater disposal. Right now, what we want to do is just talk about some protocols that are probably common sense protocols at this point. And before we wrap up, Zoback provides a nice summary of these protocols that should be adopted in general. And I think based on the discussions that we've had, it's fairly obvious that you do not want to inject in active or critically stressed faults. Even if you're in a stable cratonic area, you will find faults that are optimally oriented, critically stressed, so that if you start injecting or disposing of wastewater in areas that can reach these deeper faults, usually in the crystalline basement, then you're likely to produce seismicity. So when you're injecting wastewater, when you're disposing of wastewater, keep the pore pressure, try to minimize that. The pore pressure changes at depth because higher pore pressures lead to failures. We saw when we talked about the more circle and bringing critically stressed faults to failure. So keep that in mind. Monitor that. You need to have a good local seismic monitoring array just to make sure that you see anything. If something happens, you want to be sure you see it. And have some protocols usually referred to as green light, yellow light, red light protocols. If everything is going fine, if there isn't any significant higher magnitude earthquakes that are occurring, usually above zero, then you're operating in the green. If you begin to see some seismicity with magnitudes above zero, you might want to come back up here and reduce your injection pressures. And obviously, if you get an earthquake that's in that felt range, then you pretty much have to halt your injection activities, reduce the pressure, see if you can continue without producing further earthquakes. If further earthquakes continue to occur, there usually is a lag time between injection and earthquake activity. If continued earthquake activity is a problem in that area, you may have to abandon your well, plug it in. So these are just some general steps to follow in the development of your unconventional resources. Now, it's important to keep everyone smiling, but remember that there's a big difference in the levels of microseismicity that are associated with hydraulic fracture stimulation and the seismicity that occurs on deeper fault systems near wastewater disposal wells. So it's important to make a distinction between these two processes, these two activities, hydraulic fracture stimulation and wastewater injection. And, again, kind of be transparent and responsible in your operations. So it's important to proceed with caution, as noted in the previous slide, but also to be transparent and responsible in your activity. So in an area, this is just another example of wastewater or brine disposal causing problems and in an area. And in this particular area, earthquakes on the order of 2, not quite 3, gained a lot of attention. People felt them. And the company initially reduced the pressure. That didn't stop the earthquake activity. And they finally had to plug in the well. So keep those things in mind. This type of scenario here is meant to suggest that it could actually happen. And in fact, we really, geomechanically, I'd say it's almost, well, it's impossible to have these fractures come all the way up to the surface. You have to, because the fracture width is proportional to height, you've got an significantly increasing volume of fracture to fill, and that means that you have to maintain very high pressures in order to drive fracture height all the way up through this column of rock, and it would require enormous fluid injection volume. So another thing to keep in mind is that at shallower depths, the overburden stress is no longer your maximum compressive principal stress. It becomes the minimum stress, and so fractures roll over and they open up vertically. So we get, at some point, the fractures roll over and the overburden stress then becomes the minimum stress. Fractures open up vertically. And so fracture growth would actually be horizontal, not vertical. So a good reference on this, and we'll take a look at a graph from Fisher and Morpinski's paper that shows, now here we have, I forget how many hundreds of microseismic monitoring activities were conducted are portrayed in this graph here, but several hundred. And what you can see is as the reservoir depth increases, as we go from about 1,200 meters or so over here, down to a little bit over 8,000 feet or 2,500 meters, we can see that the frac height increases, then begins to decrease. We have some higher frac height growths down here. But for all these wells, you can kind of see that the maximum frac height growth for wells, let's say around 7,000 feet, is going to be on the order of about 1,900 feet or 586 meters. So we're nowhere close to the water table here. Now if we come on down, we see another large growth of fractures. Now whether or not these are wet, or whether the fractures that occur at this height above the reservoir are just critically stressed and they're just responding to the stress in the reservoir, we kind of suspect that's the case. But if you assume that they're wet and there's actually fluid going up to this height, that height is about 534 meters, and we're about 4,000 feet beneath a good 4,000 feet at least beneath the water table. So this is the data. This is real data. These are the kinds of fracture height growths that we see. There is no risk of the hydraulic fracture stimulation activities penetrating all the way up to the water table for wells at basically any depth at which they are being drilled for the Marcellus. And there are other graphs, if you go to Fisher's paper, that will kind of show this for other basins. So now this is just a fracture height growth versus fluid volume plot here, just kind of throwing this in. If you think about the fluids that are injected, you get to a point where there are diminishing returns. So operators are going to see that they can get maximum fracture height growth with fluid volumes of around 1,250 cubic meters. Now this equation here, you don't really have to worry about it. It's basically the relationship that's being plotted here. This is a shape factor. It's associated with the aspect ratio, which is just a ratio of the length to height. This is Young's modulus. This is the fracture volume. This is Poisson's ratio. This is the differential pressure, and so on. So this is a mathematical relationship that's being plotted. Now over here, this is an interesting one because the depth of the perforations, if we come back to this plot, this line here would represent the perforation depths. You can see that around 2,000 to 2,500 meters, we get maximum frac height growth here in this region, and then it begins to diminish as the wells and the perforations get deeper. And if you take a look at this curve here, we're down at around 2440 at a max, and that puts us right about in here. And if we go deeper than that, the frac height growth tends to drop off. So just before we leave, the discussions of unconventional resource development, just wanted to point out some additional resources. There is a U.S. Geological Survey bulletin by Nicholson and Wesson that was published in 1990, long before shale gas development activities, came into the news. And you can see that, this goes back into the 60s, the Rocky Mountain Arsenal. The Rangeley experiment was a controlled experiment. And there are several, the geysers in California, things that you may have heard about, the Matsushiro, Japan activity, which actually precipitated some fairly large, I believe some, felt magnitude seismicity. So there are several examples in here that really don't have anything at all to do with shale gas development that you may find interesting historically. The USGS also has some additional publications that you may want to check out that are associated with induced seismicity and the high rate of injection that we talked about in the central U.S. and the Oklahoma area. And in general, there are some conclusions that we can note as we wrap up here that, definitely understand what it is that you're drilling into as best as you can. 3D seismic is often indispensable in meeting that objective. It's really important that in your discussions, especially with the media, that you differentiate between hydraulic fracture treatment and wastewater injection activities, because they're really not one and the same, and often in the public's eye these two activities are identical. And it's wastewater injection which causes the large earthquakes. We did mention a couple cases. Hydraulic fracture treatment does lead to felt seismicity, but these are quite rare. And note that again that the failure that we do see occurring is on critically stressed faults and fractures that are optimally oriented for failure, and these are usually in the crystalline basement. So these are the kinds of faults that we often don't know are there, and we find out inadvertently as part of the wastewater injection, saltwater disposal, brine disposal activities. So again, wastewater disposal, critically stressed, deeper faults, usually in the crystalline basement. Felt seismicity resulting from hydraulic fracture stimulation is definitely rare. Out of the 3 million documented cases of documented hydraulic fracture stimulations, only about 1 in 43,000 is associated with felt levels of seismicity, and these have been below magnitude 3. So a very rare occurrence, and we've seen, as in the case of the Boland Shale, that this is really associated with a failure to follow some of the basic ideas of avoiding, knowing your site, avoiding injection into critically stressed faults, as was the case in the Boland, for the Boland Shale in the UK. Definitely have a good monitoring array in place. and have that traffic light system, develop something so that the public knows that you're tuned in, that you're keeping an eye on activities, and that you're prepared to react in a responsible way should something develop. And with that, I would just leave you with some references to some of the materials that we've presented, talked a little bit about. And that pretty much wraps up our discussions. And we'll continue on with other topics. Thanks for joining us.